Let's get started. Now, vector fields today, and maybe some integrals. Let's take a look at a vector field. Here's some examples of things to do with vector fields. Last time I talked about the structure of the vector field, which is the input and output, and the input can be a vector in R2 or in R3, and the output is a vector in the same domain, R2 or R3. So our vector field notation usually is a capital F with an arrow on top or boldface, depending if you're reading it somewhere. And it takes two-dimensional input and outputs a two-dimensional output. And the fact that this is not, the output is not just R, means that it's a vector as an output. And we want to look at the output as a vector. Now the input, we can also look at the input as a vector, but usually we tend to look at those as points. But I think that's really just a minor detail, because points are supposed to be vectors in standard position. But the way we're going to try to visualize this is we're going to visualize this by looking at the input as a point and a vector as a vector not in standard position but at that point. So let's try to see what that means. Let's pick a problem, maybe number 2, for an example of how we're going to try to begin to visualize these vector fields. And then once we visualize them, we'll use them as our new function to take the derivative of, to integrate, and things like that. And this particular problem, or this set of problems, is similar to a lot of the sets that we'll see. It's an introduction where we would plot points. And let's see how we get to visualize this by plotting points. And the way we're going to plot points is, like I said, the input and output business. So input is a point, so we'll call xy as your input, and then your output is a vector. I guess we'll call it xy also. Oh, we won't call it xy, we'll call it something else. Actually, maybe I don't want to do that yet. Sorry. Let's go back to this idea, and this is again from yesterday. So because our input is a point xy, we'll just say f parentheses xy, and that denotes our function notation. And so now our output is going to be a vector, and our vector is going to have two components, and the two components is based on the function that takes in as an input as x and y. So each of these two components can be labeled as, let's start with P. And Q. And both P and Q are functions of x and y. Okay, so any of those functions that we studied in chapter 14 can be good candidates for these components of this vector field. Okay? So now that I gave it a name, I'm more comfortable about making this table. So let's make this table xy, and then we'll call this PQ vector. And then we'll take this as our example over here. So our f of xy is equal to this. Now the I and j components is just another way of writing the vector in the two different components. So for this particular problem, it looks like my p function is the first component here, which is 1/2 x. And my q function is just y. Okay. Now any of those two functions can have a combination of x's and y's in them, or they can just be constants. It depends on what the problem is. But in this particular case, our p function has only an x and our q function has only a y. Okay? So now when we quote unquote plot points, we would put in values in here. 0, 0 isn't going to give us anything interesting, so I'm going to start with 1, 0. 0, 1, negative 1, 0, 0, negative 1. Let's start with those numbers or those points and then see what happens. Our output is going to be when x is equal to 0 and y is equal to 1. Our output is x is equal to 0, so the p is 0. Oh, x is equal to 1, so p is 1/2. And y is equal to 0, so q is equal to 0. Okay? Let's do that a few more times. This time x is equal to 0 and y is equal to 1. And x is equal to negative 1. Y is equal to 0. And the last one, x is equal to 0, y is equal to negative 1. All right? So those are 4 points. 4 points isn't going to give us a big enough picture, so we'll do more. But before we do more, let's take those and plot them. So let me start with the actual points. I should have got the corners too. We'll get the corners in a minute. But these are my points. And let's start with 1, 0 right here. When I have 1, 0, my vector is going to be 1/2, comma 1. Now 1/2, comma 1 as a point is right here, but as a vector, that looks like 2 points. Now that's not the vector that I want. When I'm trying to graph this, that's not the vector that I want. Well, that is a vector that I want, but I don't want it there. So what I do want is that same vector, not in standard position, but with its tail at that point that I just plotted. Does that make sense? All right, let's take a look at the next one. 1, 0, 1, 0. Again, I'm going to draw the vector in standard position, and I'll move it. I just draw it in standard position because it helps me to actually draw the vector, and then I'll take that and then I'll move it to where I want it to go. In this case, I want the tail. Whoops. I want the tail of the vector to be the point of the input. Okay? And maybe we can start getting used to being able to draw the vector displaced already instead of relying so much of it being an origin. And so here's the rest of them for this little bit. Okay, let's try those corners. So here I have to extend my list a little bit. I want to check 1, 1, negative 1, 1, negative 1, negative 1, and positive 1, negative 1. Order, this doesn't matter because I'm just plotting points semi-randomly. All right, this time I have my P for my X is equal to 1 and Y is equal to 1. There's no Y's in for P, so I'm just going to have a 1/2 there. And then my Q is Y, so that's Y is equal to 1. So that's for this point. I have a 1/2, comma 1. Okay. And then we could do the rest of them as well. It looks like I get a negative 1/2, a positive 1, negative 1/2, negative 1, positive 1/2, negative 1. So I'll have 4 more vectors. They go out like that. Okay? All right. Well, we can go on and continue plotting points, but I'm hoping you get the idea. Do you get the idea? Yeah? Question?
What's the significance of the origin where you trace back all the vector field lines?
For this particular problem, it looks like it gets traced back there, but not all vector fields are going to be like that. Any other questions? Say it again. A vector field, I don't know. What's the purpose of a vector field? In math, it just allows us to play around with another type of function. But in physics, when you talk about physics and engineering, when you talk about magnetic field or electrical field, that's a vector field. A flow line, when you have water passing through a river, and you look at the speed of the water at some point. So the speed at the turn of the river, probably the water slows down a little bit, and then as you get a long straightaway, then you get longer vectors. So it could be a flow line for some water. It could be the current going through an electric current. If you have a resistor that's slowing it down, you'll have shorter currents going after that, but then before that, you might have a lot of current passing through. You can have a magnetic field. So there's a few different applications for that. I'm not going to care too much about the applications. Say it again? These blue dots? No, it's just random. And zeros and ones are the easiest number I can think of. But you can certainly use any number you want and then get these points. In fact, there's some where, something like 2 and 5 might be more appropriate than zeros and ones, but that's what I decided on. Okay. So a vector field kind of gives you the flow of certain things. And for most cases, I'll probably use the water analogy, the flow of water going somewhere. And once in a while, I'll talk about electricity and magnetism stuff, but I'm not going to talk about electricity and magnetism. I'm just going to pretend to talk about it.
Is it the Untitled function?
Say it again?
Is the Untitled function?
This is our new type of function. So back in pre-calculus, we have regular f of x functions. And then when we came here, we have r of t, and that as a vector function. And then we have f of x, y. That's our second major function, and now this is our third and last major function. Maybe not the last. All right. Well, as much as drawing this by hand is fun, you can always find something to graph this for you. So Mathematica will do this for you easily. Graphing calculator, the program will do this for you. And for the free version, I've talked about this program a lot because it allows you to visualize things in 3 dimensions, and it would be good to be able to do that. So let's let's see how we can do this. Now this is a 3D plotter, so the name suggests that you're going to do things in 3 dimensions, which would be good for 3-dimensional vector fields. We'll take a look at 3-dimensional vector field also. But there might be some time where you just really want to look at a 2-dimensional vector field. And so for those cases, what you can do in this particular program is just ignore the 3rd dimension. So if I go to graph, there's a add a vector field option. That seems like it's the appropriate thing to do, right? And so what was our vector field? Our vector field is 1/2 x. Can I get there? Can I change it? I can't change it. Boy, I don't know. Barbed. I was just going to talk about how cool this was, but now I can't change these values. Well, this isn't 1/2 x comma y, it's x comma y. But if you wanted to do this and look at it from a 2-dimensional point of view, just look at it from the top. What? Oh. Ha, it's even better. Okay, so this is what we would see. This is true. All right. This thing just let me down, so I'm going to go back to my graphing calculator. So the hard part about these programs is that they may scale their vectors, because the length of the vector actually does matter a little bit, but if they scale it so that you kind of get to see the big picture, and really all you want to do is compare from one portion of the graph to another portion of the graph. So to do this in this graphing calculator program, you have to label the dx, dy business. And so it's almost like the parametric curves. And then we have a 1/2 x and a y. So if we graph this, this looks a little bit more representative of the graph that we're supposed to be looking at. I mean, if you compare this to the graph that they have here in the 3D plotter, the graph in the 3D plotter is just x, y. So the graph in blue, I don't know if you guys can see it. The graph in blue, that's not blue. This graph that we're looking at is the graph that we saw in the 3D plotter, and the graph in blue is a graph that we actually want. So it's a little bit different, and you notice it's a little bit steeper. These lines look a little bit steeper than the other ones. So this is really how this graph should look like. Yeah?
Is this like the same thing as a direction field from chapter 9? In separable equations, the direction? Is that why you use dy, dx, or dx, dy?
Kind of, yeah. There's certainly a relationship between directional fields and this. So you can also see some graphs, but you can move things around to see how the arrows change. And it's hard to see because the arrows are so small. So I haven't found a good way to scale this yet. But there should be a way to scale the arrows. All I know is that I move further away, the arrows are going to get larger than if I get closer to the origin. And that makes sense because your x and y values are larger also. But again, this is not drawn to scale. This is drawn to proportion with all the rest of the other graphs. All right. So I don't know if it's worth. Yeah, zooming in and out doesn't help either. With respect to the origin. So it still kind of looks the same. In fact, I might be losing some. So, but the key is to try to figure out, by the equation that you're given, try to figure out with maybe a handful, maybe 4 to 8 points like we have here, try to figure out the general shape of this, and then you should be able to identify the graph. And you'll have a couple of multiple choice problems in your homework where you have the equation of the vector field, and then you have a couple of drawings to choose from, and you figure out which one's which. 3 dimensions, you can also do things in 3 dimensions. So drawing this by hand is going to be a little bit more difficult, but some of these are pretty obvious. Like number 9, for example. Let's take number 9 and see if we can do that problem. So this takes a 3-dimensional point and outputs a 3-dimensional vector, and the vector is just going to be in the k direction. So already, because of this vector only in the k direction, how should this vector field look like? Arrows are going to be pointing directly up and down, okay, because of the k. And the arrows pointing up and down depends on x. Whether x is positive or negative, it's going to be pointing up and down. Okay? Right? Okay. So we can plot a few points. So really all we're concerned about is finding out what x is equal to. So if we plot a few points like 1, 0, 0, 0, 1, 0, 0, 0, 1, that's just a handful for now. 1, 0, 0 is here, 0, 1, 0 is here, 0, 0, 1 is here. And our vectors will just be, for this one, it's just be 0, 0, 1. And these other ones would be what? Just be zeros because there's the x is equal to 0, so that's not going to contribute anything. So I have one vector here that goes up by 1, and then all these other vectors have nothing. So if I have another point 1, 0, or 1, 1, 0, I would be over here somewhere. 1, 1, 0, I'd be over here. And my vector for that is going to be what? 0, 0, 1. So be going up. Okay. So if I go further out into x, what's going to happen? I'll have, like if I go x is equal to 2, I will have 0, 0, 2. I'll have longer vectors. Right? If I go in the opposite direction, negative x back here, what's going to happen to these vectors? They'll be pointing down because the x's would be negative. Okay? So let me see if we can do another point over here. Gets a little messy. So, again, use a program. You could probably Google an app or something that's an online program that would help you draw these vector fields. Let's see it being drawn. Let's see if that 3D plotter is going to help. Gosh, it doesn't help if I can't. Never mind. Well, I'll show you an example of a three-dimensional plot here. So our graph is a little boring, but can't even really see it. Well, that's how it would look like in 3 dimensions. All right, so that's a vector field. Okay? Yeah?
When you go negative y, like to the left of the x-axis, there's still going to be positive.
Yeah, they're still going to be going straight up or down because y has no bearing in it. So it only depends on your position of the x. So whatever you see in the negative y would be the same thing you would see in the positive y. And even the going up and down the z, it's not going to change either. So it's all just going to be dependent on x for this particular one. All right. So you have some matching problems here. So another interesting thing that's for us to look at is that this is how a vector field is defined, right? It's defined by some function that has different components of the function separated as functions of multiple variables. And so we've seen something like this before where we have a vector that has functions of x and y on either side, on each component. We actually saw it in 3 dimensions as well. Do you vaguely remember where that came from? Yeah, I don't know if I'm phrasing the question correctly. We've seen something where we come up with a function or the vector that has 2 different functions on either side. And the question is, how did we get that? What? The gradient. Remember that? So when we say the gradient, we're talking about the gradient of a scalar function. I want you to look at this f and this f and convince yourself that those are different f's. Not only are they different letters, capital and lowercase, this one has an arrow on top, this one doesn't, and that's the big difference. Okay? So the gradient of this function turns out to be a vector. Not only a vector, but a vector with x's and y's in it. So that would qualify as a vector field. So let's take a look at an example of one of these things. Say f of x, y is equal to, I don't know, something easy or something hard. Well, let's just say x squared plus 2xy plus y to the third. Right? So this is a function. By the way, I'm going to start referring to this as not a multivariate function, which it is, but I'm going to start referring to this as a scalar function. And the name scalar function is based on the output. The output is just a scalar. I want that to be different from a vector function where the output is a vector. Okay, so we have a scalar function here. Now let's take the gradient of that. And the gradient of this is a vector whose components are just the first derivatives of with respect to x and with respect to y. So this would be 2x plus 2y, and then it would be with respect to y 2x plus 3y squared. Now if we look at this as P and Q, we essentially have a vector field. Right? So the fact that this comes from a gradient says that we can actually call it a gradient field. So if you have a gradient field, oops, the I goes before the E, gradient field. Notice the gradient field is denoted by capital F. It turns out that capital F is actually equal to the gradient of little f. And this relationship will, for us is going to become important, because if you have this relationship is a true relationship between capital F and some little f, then we have a gradient field. And that is also called a conservative field. I should type all this stuff. When I'm writing too much, I should just type it. Brian?
This shows the vector of the gradient equals the gradient that exponents that conservative.
Yeah.
You said that convention shows something different.
Yeah. What's different? The two functions that are different is the big F and little f.
So all little f's can be the big F, but not all big f's can be the little f.
No. If you put this symbol in front of the little f, that could be the big F. Yeah. Almost. That was a good question. Did you hear Caesar's question? He said, if you graph of these simultaneously, would the gradients be perpendicular to the surfaces? And I said, almost. How should that question be changed so that it would be, the answer would be yes? Well, that would be the case too. What? Perpendicular to the level curves. Yes. But first, so back to Brian. Brian said something. He said this could be that, but not that. Could be that, this, that. Yeah. So it turns out, I think what you're trying to say there, if I may put words into your mouth, that a gradient field is a vector field. But if you have a vector field, it may not necessarily be a gradient field. That's what he meant to say. He's nodding his head, yeah. So I think it would be good to take a look at some examples of gradient fields or vector fields that are gradient fields and vector fields that are not gradient fields. I should have prepared an example. I'm trying to do these integrals in my head. There's two standard examples of things. I can't remember what they are. All right, let's just see if I can make one up. All right, let's hope one of these is a vector field and one is not. I'm not sure what's going to happen. And then we'll draw it once we figure it out. So if we have a vector field that looks like this, we're not quite sure that this is a gradient field. So that was the thing that Brian was trying to say. If one thing, then the other, but it doesn't go backwards. So we want to know if this is, in fact, a gradient field. So the question is, can we find little f such that the gradient of little f will equal to the big F, and the big F has an arrow on top. Right? So we want to know, is there a function so that when we take the gradient, is there a function little f so that when we take the gradient of that, it's actually going to equal to this? Well, how would you get the gradient field anyways? How would you get the vector field? Partial derivatives, right? So we took this thing, we've been calling this P of x and Q of x. And if this was in fact the gradient field, then P should actually equal to the derivative of little f with respect to x, shouldn't it? And then Q should actually equal to the derivative of little f with respect to y. And if we can find out what little f is based on this fact, then we actually have a gradient field. Does that make sense? If it's a gradient field, it's a gradient vector, which means it came from a function whose derivative with respect to x is in the first component, the derivative with respect to y is in the second component. So now I want to essentially do the antiderivative. So from y, if I take the antiderivative of y with respect to x, then I could possibly obtain my original function f. Yeah? This is an indefinite integral, so we're going to have constants here. So let's talk about that constant. So the antiderivative of y is 1/2 y squared plus some constant, right? Oh. So what should it be? xy. So we have a constant, but the constant is a constant with respect to x. So the constant could possibly have a y in it, right? If this had a y in it, and we took the derivative of that, then with respect to x, then the derivative of this thing with respect to x would make this y equal to 0, the derivative of something with a y in it, as long as there's no x's. So I would say my f function should be x, y plus some constant that may include y's in it, because it's constant with respect to x. Okay? So that's approaching it from the P side. Let's approach it from the Q side. According to this derivative here was a derivative of the original function with respect to y. So if we take the antiderivative and go backwards, we should obtain our original function. What's the antiderivative of negative x with respect to y? Negative xy plus some constant with respect to x. So now what we want to do is we want to match these two functions and then match any derivatives that might have disappeared along the way. But if you look at these two functions, can they be matched? Are they the same? Looks like xy compared to negative xy can never happen. So I would have to say that this is not a gradient field. Okay, you guys are making funny faces, but that's good, I think. So, yeah. I integrated because if we were saying that this is supposed to be the gradient, that means that the original function came from a derivative of something, and we want to obtain the original function. Well, with the constants, if we need to wiggle some constants around, then we'll need to wiggle constants around. But in this case, the combination of x and y here says that one's negative and one's positive, so that can't ever happen. We'll see in the next example how those constants might play in to this. All right, now we'll ask the same question. Can we find some function f that will give us this as a gradient? So let's go through the same steps. We'll assign the first component as if it was p, which is the derivative of our original function that we're looking for, if it exists. The derivative of that with respect to x, and this is q, which is the derivative of the original function with respect to y. So we're saying if we take the antiderivative of x with respect to x, that could be our possible function, right? And so this turns out to be 1/2 x squared. Plus, indefinite integral, there might be some y constants there, because with respect to x, y is a constant. And let's take the q function and take the antiderivative of that q function, this time with respect to y. So that's 1/2 y squared, but we ignore the other constants that might have an x in it. So now these two clearly are not equal to each other, but they are constants with respect to the other one. Right? So if I say my f function might actually be 1/2 x squared plus some constant with a y in it, well, how about let's just say 1/2 y squared? And maybe another constant. Let's just throw in another constant for good measure. This time it's a real constant with no variables. Then this could have been, is, maybe, yes, it is your original f function whose gradient is actually equal to this. No, that's a good question. And this is a good question to try to figure out when we have our capital F and little f. This here is a scalar function whose output is a scalar. The input is x and y, the output is a number. So this is a scalar function. This is capital F, a vector field that has components. But it's also a gradient field because we just found out by finding this function, if you were to take the gradient of this function, this is actually going to exactly equal to the original vector field that we were working with. Okay? So, the graphs. We're all looking forward to the graphs. So now that we know that this is a gradient field, if we take this function right here and graph it, it's not going to help us any.
It's like an infinite amount of graphs that you can have.
Yeah, you can have an infinite amount of graphs, huh? So, how should we deal with that?
Just call it 0.
Let's see if this will work. F of xy is equal to 1/2 x squared plus 1/2 y squared plus an infinite number of constants. Let's pick a number. 0. Let's pick 2 to make it seem exciting. What am I going to do with this? It's all the way up there. So it's basically this paraboloid that's been moved up, right? But again, we don't want to see this in 3 dimensions. This isn't going to help us in 3 dimensions. So what we want to do is we want to take a look at our level curves. So let's take our function and make level curves out of them. And to do this, I'll try to do a split screen. And equals 0 probably won't work because this graph doesn't touch 0, right? So let's make it equal to at least 2, maybe 3. Actually, 2 would just be a point. Three would give us something a little bit better to look at. So with 4. Okay, so these are sample level curves. You can see that the level curves are just going to be a bunch of circles. So let's draw the gradient field. Oh, I don't know if I can draw the gradient field. What's the gradient field again? X, Y, just X and Y. Let's see if it'll draw it. Nope. There it goes. So if you look at the vectors coming out of the vector field, they look like they're all going to be perpendicular to the level curve. And if you want to take one of these vectors and put it right on the level curve, you can see that wherever you are on the level curve, it looks like it'll end up being perpendicular to that. The surface is 3-dimensional, and the gradient that we have here is 2-dimensional. So my answer to that would have to be no. This picture? No, this picture is totally 2-dimensional. The vector is still 2-dimensional. You can. To the level surface. So the vector, the graph or the function itself that we would be looking at is a 4-dimensional function, which we can't visualize, but we chop it down to 3-dimensional level surface, and the 3-dimensional gradient would be perpendicular to the 3-dimensional level curve of a 4-dimensional surface. And that was coming when as I was saying it. Lisa, did you have your hand up?
Yeah, why do you need the primes on the DX?
Oh, this is just for this particular program. It allows me to do a split screen, and the primes will start drawing things on a different graph, like here. So all these things with a prime in it are drawn here, and things without a prime in it are drawn on this side. So back to the gradient. The gradient is the same dimension as the input. So for a function z is equal to f of x, y, the input is 2-dimensional. So your gradient's 2-dimensional. So it all comes down to the level curve. Okay, if you want to see surfaces, then we imagine something happening in 3 dimensions. You can always throw in that -1. What am I talking about? I don't know. What? No, I do know what I'm talking about when I say -1. I was just hoping that you would too. It's an inside joke. Well, see, Renee and Alex did that lecture where I would have introduced the -1 and then made a big deal out of it. So now it's an inside joke with myself. But joking aside, where is that? -1. So when I say just throw in a -1, you got a 2-dimensional vector for your gradient, you throw in a -1 for your z component, now you have a normal vector. Okay? So if you want to go to 3 dimensions with this idea, then that's where you go. Take -1 with you. All right, let's see if we can find another homework problem. We're dealing a lot with 2 dimensions here, and the book approached it with 2 dimensions. I think the way the book should have done this is introduced a couple of other derivatives that would be useful for us. And the 2 other derivatives that we're going to learn about, it's called a div and a curl, and they have something to do with your gradient notation. And when I say gradient notation, is that the notation that we use for the gradient, that upside down triangle, plays a part into the definition and the computation of these other derivatives. So I was going to talk about flow lines, but that's like differential equations, so we might come back to the idea of flow lines later. But for now, let's see if we can go forward a little bit, looking ahead in one of the other sections. This gradient business is denoted by this thing, right? And then what we get out of this is we get the partial of f with respect to x, the partial of f with respect to y, and if we have a third component, we go the partial of z. Notice I'm writing this a little bit strangely. I'm kind of writing the f, it kind of started up close to the top and it started fading down. But f, if we think of f as a scalar, we could almost think about taking this out. It's kind of silly to think about it that way, but maybe let's just pretend that we can take it out. So in terms of vector talk, what would you call this vector times f? A what? No. What? No. What? There was like 3 things everybody said at the same time, and they all were different, so I just wanted to see if I get everything. What? What? Scalic vector. We called that something else, didn't we? Scalar multiplication. I asked for what? Is that what you said? Scalar multiplication? Oh, pari. What did you say? No, okay, sorry. Well, I won't look at you. So the thing is that somebody's managed to split this up into a scalar and a vector, which means now we're kind of responsible for this thing by itself, or we should be able to look at this thing as a thing by itself, right? This thing, it's not, yeah? Yes, operators. So let me rewrite it, the same thing with I, J's, and K's. I guess this should be a plus, right? So it doesn't matter how you write it. And Caesar's right. This is, in fact, called an operator. And this, apparently, is called a del operator. I don't know. So we could treat it as if it was a vector. And all we've had so far is a scalar function. So the only thing we could do with a vector and a scalar is scalar multiplication. And it looks like when we scalar multiply, I want to say scalar multiply in quotes, when we do a scalar multiplication with this operator and this function, we actually got the gradient. Okay? But now we have a new type of function, right? We have a vector. What can you do with a vector? Cross them, dot them, right? We can dot this and cross this. So we can take our del operator, which is a vector, and we can dot it with your vector field. We could take this vector field and cross it. So now we couldn't do that before because the dot product and the cross product works only for vectors. So now we have a vector operator, quote, operator, and that's not quote, a vector operator that we're going to, quote, dot. That one's a quote. So if we imagine taking our del operator and we dot it with a vector field, and let's rewrite this vector field as I was going to say P and Q, but that's only for 2 dimensions. What's after Q? R. Assuming that they're all functions of 3 variables now, functions of x, y, and z, then we can get this, the partial of P with respect to x. What do you get when you dot product? You get a scalar, so there's a plus partial of Q with respect to y plus partial of R with respect to z. So this is another function. This is a derivative of some sort. This is a derivative of a vector field. Question? Well, that's a
So you're just taking arbitrary?
arbitrary f.
Oh, okay.
Yeah. But that is a good question for the next one. You should have asked that question after this one. But we don't have that much time anymore. We don't have time at all. What?
Are we looking at this as a gradient?
No. So these, by the way, are called a div and a curl. And so the second one over here, you'd have to set up the I, J, K, partial with respect to X, partial with respect to Y, partial with respect to Z, and then P, Q, R. So this is going to be a little bit more work to do. Say it again? Unless you can program this into your calculator, then good for you. But the result here will play an important part in looking at gradient fields. So these are arbitrary vectors, vector fields, and not necessarily gradient fields. But for a gradient field, there's something special that happens here. Okay?
You're taking a gradient of a gradient.
You're taking the curl of a gradient. Yeah.
If that was two-dimensional and we had a space curve and we applied that analysis with the div, what is that? What do we get trapped?
I don't know. Okay, really quickly, the div graphically gives you the expansion or compression as you move along the flow of the gradient field, of the vector field. And the curl gives you the rotation. The rotation as you move along a vector field. Now there's going to be a lot more pictures when we get to this section, but this is a few sections ahead. And so sometimes the curl is called the rotation, and the div is called the divergence. All right, more next time.